Hello everyone, I'm Bondi. I'm going to talk about our work, fast, flexible, and comprehensive bug detection for persistent memory programs. This work is in collaboration between the Hunan University and the University of California, Merced. Persistent memory are expected to recover to a consistent state and be able to resume execution in the event of a failure. PM programs must guarantee crash consistency. However, developing PM programs with crash consistency is challenging. Some bugs are caused by the missing data durability or violating ordering constraints. For example, if the program misses the write back or fancy instructions, the updating becomes volatile. For ordering constraints, if the program misses fancy instructions, X and Y may be reordered. Meanwhile, various persistent models have different constraints for data durability and order constraints that make developing crash consistency programs more complex. To solve it, we require PM-specific debugging tools to help us. Next, let's take a look at how prior tools solve this problem. First, the manual or automatically instrument PM programs. Then, they use a tree-like structure, such as the AVL tree, to bookkeeping store, write back, and fetch instruction one by one. I use an example to simply show this process. When debugging tools encounter a write to C, debugging tools record the related location information such as address and size and inside this information into the tree instruction. Then reorganize the tree to rebalance it. The tree reorganization is in order to get the faster search. If debugging tools encounter a write back instruction for location B, the search and update information of location B in tree instruction and mark the state of location B as flushed. When fancy instruction come in, debugging tool search and deleted nodes whose states are flushed, because the durability is guaranteed at the fence, then reorganization the tree. In addition, if debugging tools encounter manual or automatically inserted checker, they check the information nodes in tree structure and reporting them who violated checker rule that defined by checker. As a result, to debugging memory cache with 1 million persistent operation, prior tools such as inter-SP memory check cause 218 times slowdown, and the XF detector cause 1,000 times slowdown. Such large performance overhead largely comes from the bookkeeping, 82% of total overhead on average in P-memory check. To gain the high performance, PM tests the manual instruments and selective checker to reduce the bookkeeping overhead, but cause less bug coverage. Prior tools face a fundamental trade-off between the performance and the bug coverage. Therefore, we want a fast and flexible PM debugger with a more bug coverage. In this work, we first characterize PM programs in terms of how store, write by, and fetch instruction happen, and get 3 PM program patterns. Then, depending on these patterns, we design the PM debugger, which use PM-aware data structures to achieve faster bookkeeping of memory locations and persistence. In addition, PM debugger defines 9 checking rules and supports 2 relaxed persistent models, so it supplies more bug coverage. As a result, PM debugger requires less user annotations and less debugging time. PM debugger found 19 new bugs in memory cache and 2 new bugs in PMDK. All bugs are reported to developers, and developers confirm them. Next, I introduce our PM characterization study. To study PM characterizations, we use PM benchmarks collected from the XF detector, PMDK, PM test, and Whisper. These benchmarks cover the most common usage, including PM data structures, database, and memory caching. These benchmarks also cover the various persistent models. To cover the various read and write patterns, we run YCSB against memory cache. We first study characterization of fancy instructions in PM programs. We found the durability of 77.7% of stores is guaranteed by the nearest fence, and the durability of 4.6% of stores is guaranteed by the second fence. Based on the above observations, we identified the first PM program pattern. For most store, the data durability is guaranteed by the nearest fence. We can get the inspiration from this pattern. Tree reorganization in the traditional bookkeeping has few opportunities to gain the performance benefits, because the information of the most store is deleted in a short term. Then we study characterization of store instructions in PM programs. We firstly split stored instructions into intervals by write-back instructions, and store instructions between two neighbor write-back instructions forms a write-back interval. If a single write-back persists or stores in a write-back interval, we call it as a collective write-back. If a single write-back only persists partial stores in a write-back interval, we call it as a dispersed write-back. As a result, more than 71% of all write-back intervals have been collective flush. Based on the above observations, we identified the second PM program pattern. Stores in a write-back interval are highly likely to be flushed together by the same single write-back. We can get inspiration from this pattern. It's promising to collectively maintain and update our persistent states of memory locations for high performance. Last, we counted the number of stores, write-back, and fancy instructions, and found in most of benchmarks, stores account for 70% of the 3 instructions. In all benchmarks, store account for at least 14.2%. Based on the above observations, we identified the third PM program pattern. Store happens more frequently than write-back and fancy instructions, so we must efficiently process the store instructions. Next, I will introduce our debugging tool, PM Debugger. PM Debugger directly debugs binary files of the PM programs and instruments memory stores, write-back, and fancy instructions. PM Debugger splits the instruction trees into intervals by fancy instructions. We call it as a fancy interval. Within a fancy interval, there is at least one write-back interval. For data structure, PM Debugger uses a PM-aware data structure for bookkeeping, including a memory location array and an AVL tree. In a memory location array, it consists of the metadata and memory location information. Memory location information records the information of a store. Metadata records the information of a write-back interval. The AVL tree is used to receive the memory location information from the array. Using the array structure, memory location information can be directly inserted into the array structure without reorganization. Such fast processing of stores is necessary due to pattern 3. Use the metadata. PM debuggers enable fast querying and collection updates memory location information when processing write-back instructions. Pattern 2 suggests this design. When processing fancy instruction, PM debugger can simply invalidate metadata to enable much faster memory location information deletions and redistributing the some memory location information from the array to AVL tree to gain the long-term benefits of the quick searching. This design is driven by pattern 1. Meanwhile, PM debugger automatically verifies the information to chicken bugs according to the defined chicken rules. Then, I give more detail for our PM-aware data structure. Each memory location information in the array and AVL tree is collected from a store instruction and includes the memory location address, location size, and the flushing state. The flushing state indicates whether the memory location is persisted by a write-back instruction or not. The metadata for a write-back interval has the following information: the beginning and end of the interval, showed as the array indices, the address range of the memory locations collected in the write-back interval, showed as the minimum and the maximum addresses of the address range. The next pointer, a pointer, points to the next metadata. Last, the flushing state of a write-back interval, used to indicate the write-back interval is a collective write-back or dispersed write-back or not write-back. Now, I show how PM debugger processes the store instructions. PM debugger performs 2 steps. First, add memory location information into the memory location information array. Then, update the metadata for the currently write-back interval in the memory location information array. The table shows the metadata. We assume the index of the last 3 elements is 5, so we record the start index as 5 and the end index as 7. The minimum address is the beginning of the location A1, and the maximum address is the end of the location of A3. Because of this metadata is the last one, so the next pointer is null. The flushing state of this write-back interval is marked as not write-back. Then, I show how PM debugger processes write-back instructions. PM debugger first updates memory location information in the array. To update the states in the array, PM debugger travels the metadata one by one. If this write-back interval is a collective write-back interval, PM debugger directly marks the flush states in the metadata as a collective write-back. If this write-back interval is a dispersed write-back interval, we can see B1 cannot be flushed by this write-back instruction. So, PM debugger marks the flush states in the metadata as a dispersed write-back, and then go further marking every memory location information one by one. After finishing the array, PM debugger goes to travel the AVL tree structure. Finally, PM debugger creates a new metadata for next write-back interval and updates the next pointer. When processing fancy instructions, PM debugger removes the memory location information who have been flushed by the write-back instruction. PM debugger first travels the AVL tree, then the array. In the array, the way is similar to processing the write-back instructions. If the write-back interval is marked as a collective write-back, PM debugger simply invalidates the metadata to delete this invalid memory location information. If the flushing state in the metadata is marked as a dispersed write-back or not write-back, PM debugger invalidates metadata, then we distribute the remaining memory location information into AVL tree. PM Debugger also supports debugging in a relaxed persistent models. To debug a program using an iPorch persistent model, PM Debugger adds a flag to indicate if the store instruction comes from an iPorch section. This flag is used to help PM Debugger verify the checking rules. To debug a program using a strand persistent model, PM Debugger sets up a memory location information array and an AVL tree for each strand section, so the detections for different strands can happen in parallel. PM Debugger defines 9 checking rules to detect the following 9 bugs. 5 of them are common to all persistent models, and 4 of them are specific to the relaxed persistent models. Leveraging the data structures and algorithms to process instructions, PM Debugger has the flexibility of adding rules to strengthen bug detection functionality. Next, I will show our evaluation results. We evaluate PM Debugger on a machine with the Intel Optane DC persistent memory module. To evaluate PM Debugger, we choose 8 micro benchmarks and 2 real-world workloads, memory cache and radius. The first evaluation shows the performance. The y-axis shows the performance speedup of PM Debugger over pmemory check. The finger shows the overall speedup. As a result, for micro benchmarks, PM Debugger gains average 2.2 times performance improvement. For memory cache, PM Debugger gains 4.7 times performance improvement. For radius, PM Debugger gains 2.1 times performance improvements. Compared with XF detector, PM Debugger achieves 49.3 times performance improvement. Compared with PM test, PM Debugger has less than 2 times slowdown. However, PM test has less bug coverage and relies on the programmer to annotate the program, which causes a heavy burden for a programmer. Next, we show the bug detection capability. We use a dataset containing 78 bugs. 68 of these bugs come from a bug evaluation suite. Because the bug evaluation suites do not include these bugs specific to the relaxed persistent models, we add 10 extra synthetic bugs. PM Debugger has the best bug detection capability. In addition, PM Debugger found 21 new bugs in memory cache and PMDK. These bugs were not reported before. All bugs are reported to developers, and the developers confirm the bugs. In conclusion, we characterize PM programs and get 3 PM program patterns, shedding light on the efficiency design of a PM debugger. Then, we introduce a fast, flexible, and comprehensive PM debugger, designed based on the PM program characterizations. As a result, compared with the XF detector and pmemory check, PM debugger leads to 49.3 times and 2.5 times performance improvement on average. Compared with PM test optimized for high performance, PM debugger achieved comparable performance without heavily relying on programmer annotations and detects 38 more bugs. In addition, PM debugger detects 19 new bugs in memory cache and 2 new bugs in PMDK. Last, our artifacts get all SM badges, and is available at our GitHub. Thanks.